What if an old coconut tree could become strong brown paper instead of simply becoming waste? Today, we follow that forgotten trunk through machines, heat, chemicals, water, pressure, and precision until it becomes paper. And here's what nobody tells you. The hardest part isn't making paper, but turning irregular plant material into reliable fiber. The journey begins where coconut plantations eventually reach the end of their productive life instead of sending every trunk toward low-value disposal. Researchers have explored its cellulose-rich structure as a papermaking resource. Studies have reported coconut trunk fibers around 1.94 millimeters long, making their structure surprisingly interesting for pulp production. But before any fiber reaches a paper machine, the trunk must survive a surprisingly brutal preparation stage. Because one mistake at the beginning can follow the material through every machine that comes afterward. So what happens first when these massive trunks finally enter the processing line? First, workers inspect each trunk for dirt, stones, metal, excessive moisture, and sections unsuitable for processing. The usable trunks are then cut into manageable sections before entering the next stage. Those sections are chipped into smaller pieces, increasing surface area so later chemicals can reach the fiber structure more effectively. Then screened separate oversized pieces from the chip size. The pulping system can handle this. Simple-looking sorting step quietly determines how evenly the cooking stage will work, and the material isn't uniform like ordinary industrial wood. Coconut trunks can vary dramatically from section to section. That variability is one reason industrial trials carefully control chip size, moisture, chemical dosage, and cooking time. In one reported Kraft study, active alkali reached 15.6%. With cooking lasting 3 hours, that study reported about 44.3% total pulp yield under those tested conditions, but that number belongs to a specific study, not a universal factory setting. And that's an important distinction because real mills adjust their recipes according to raw material, equipment, paper grade, and environmental requirements. And now the chopped coconut material reaches the stage where its natural structure begins to disappear. Inside the digester, heat and alkaline chemicals attack the bonds holding lignin around the cellulose fibers. The goal isn't to destroy cellulose. It's to free those valuable fibers while removing unwanted binding material. As cooking continues, the hard chips soften, darken, and gradually transform into a fibrous mass. 3 hours of cooking appeared in one published coconut trunk Kraft experiment, showing how substantial this transformation can be. When cooking finishes, the pulp must leave the digester without carrying unwanted debris into the next machine. Screens catch uncooked pieces, knots, and oversized fragments while usable fibers continue forward. Then washing removes spent chemicals and dissolved material, preparing the fibers for controlled refining. At this point, what looked like chunks of palm has become something completely different. Wet, tangled cellulose fiber. But loose fibers alone cannot become strong paper. They must be refined so they bond together efficiently. Refining changes fiber surfaces, helping neighboring strands grip each other. When the sheet eventually dries, too little refining can weaken the sheet, while too much can damage drainage and slow production. So operators tune the refining system until the fibers balance strength, formation, drainage, and machine speed. Now the fiber slurry is diluted with water until it can flow evenly across the forming section. The mixture may look like muddy water, but hidden inside are thousands of tiny fibers waiting to form a sheet. And this is where the process becomes almost magical. Liquid suddenly starts turning into a continuous paper web. A moving forming fabric spreads the fibers while water drains through tiny openings beneath the developing sheet. The sheet is fragile here, so even small disturbances can create holes, streaks, or uneven formation. That is why papermaking is less about one giant machine and more about controlling thousands of tiny variables. Next, massive press rolls squeeze water from the wet web and dramatically increase its solids content. The sound changes here too, from watery splashing toward the deeper mechanical rhythm of compressed fiber. Then heated drier cylinders take over, removing the remaining moisture through controlled contact and evaporation. The wet sheet gradually becomes dry, flatter, stronger, and unmistakably recognizable as paper. But natural Kraft paper isn't finished simply because it looks dry. Its surface, moisture, thickness, strength, and formation still need careful control before anyone can package it. And now comes a transformation most viewers never notice. Enormous rolls become manageable. Commercial paper slitting knives cut the master roll into exact widths required for bags, wrapping, packaging, or other applications. The machine must keep tension stable, because one uncontrolled variation can wrinkle an otherwise perfect roll finally. Automated winders build compact rolls with carefully controlled edges and tension, but before those rolls leave, the factory still has one question: are they actually good enough? Modern paper production can combine human judgment with sensors, cameras, scanners, and automated control systems. Optical systems can watch the moving web continuously, searching for visible defects while production never stops. Tiny holes, streaks, dirt, wrinkles, moisture differences, and uneven formation can all threaten the final grade. The factory doesn't simply ask whether paper exists. It asks whether every important property stays inside specification. Thickness is measured precisely because packaging machines depend on predictable paper behavior. Moisture matters too, because too much or too little water changes strength, flexibility, and processing behavior. Then tensile testing pulls samples until their fibers finally give way. That single test reveals how effectively thousands of individual fibers join together during drying. Burst and tear testing provide another perspective for packaging grades. Strength matters because paper may face folding, pulling, stacking, impact, and repeated handling, revealing how paper handles sudden forces and concentrated damage. Yet technology has a limit. Machines measure patterns, while experienced workers often recognize problems before instruments explain them. A trained operator can notice a change in sound, feel, vibration, or surface long before a serious defect appears. That's the hidden partnership inside advanced manufacturing. Human experience guiding machines that can measure far more than humans can, and once quality passes, the final rolls are wrapped, labeled, tracked, and prepared for transportation. What began as a rough tropical trunk is now standardized industrial material ready for another manufacturing journey. The coconut trunk paper story sits inside something much bigger. A global paper industry producing hundreds of millions of tons. FAO reports about 423 million tons of paper and paperboard production worldwide in 2024. The same FAO data puts global wood pulp production near 189 million tons that year. China led paper and paperboard production in 2024, followed by the United States, India, Japan, and Germany. Together, those countries represented roughly 2/3 of global paper and paperboard output in the FAO's 2024 shares. But coconut trunk paper is still a niche pathway, not a replacement for the entire conventional pulp industry. Its real promise may come from finding useful value in agricultural material that would otherwise have limited applications, and that's why researchers continue testing agricultural fibers, searching for alternatives that fit local resources and manufacturing conditions. Did you know coconut trunk research has examined not only paper, but boards, furniture, energy products, and other uses? Did you know one published study found coconut trunk chemistry and fiber dimensions promising for pulp and paper? And here's another surprise. Global paper production has grown enormously since the early decades of modern industrial papermaking. FAO's long-running statistics track pulp, paper, recovered fiber, and other forest products across more than 6 decades. Recovered paper has also become enormous globally, reaching about 241 million tons in 2024. That means the future of paper isn't only about new fiber, it is increasingly about using old fiber again. For coconut trunks, the challenge is proving that processing costs, fiber quality, logistics, and environmental gains make commercial sense. Transport matters because bulky trunks contain water and biomass that must travel before processing begins. That makes local processing especially interesting, because shorter supply chains can reduce unnecessary movement of bulky raw material. Energy and water use also matter, because every sustainable claim must consider the entire production system. A material can be renewable and still require careful management of chemicals, water, energy, emissions, and waste. That's the difference between simply calling something natural and actually measuring its environmental performance. And this is where the future gets interesting. Better processing could turn more agricultural residues into useful fiber, but scaling any alternative fiber means proving consistency, economics, safety, performance, and supply year after year. So the future may not replace conventional paper overnight. It may gradually add smarter sources to the fiber mix. Now look back at that forgotten coconut trunk sitting outside the factory. It passed through cutting, screening, cooking, washing, refining, forming, pressing, drying, testing, and winding. What looked like ordinary biomass became a carefully engineered sheet with measurable industrial performance. And that transformation reminds us that manufacturing isn't simply about machines. It's about understanding materials. It is about learning what nature already built, then finding ways to shape it responsibly. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.